cloud. And I'm going to share my screen. We're going to head to my class website, updated today for the week, pretty much. And let's go on and finish our organic chemistry reactions, or organic chemistry in general. So share my screen, always telling you what I'm doing, I guess. And we're going to go to one of these two places, not AP Bio, AP Chem. All right, and there we go in all of our glory. All right. I don't think I need that there. Okay, so what we're gonna do is, no, we gotta refresh that screen. Okay. All right, any case, here we go. All right, so today's Tuesday, the 9th of June. Oh my gosh, the year is, I think next week is my last week of teaching, I think. Any case, I should know that. But any case, today's assignment is just following along with me for the last little lecture of organic reactions. We started it. We're gonna do a couple of demonstrations. I'm gonna show you what I've done in videos in the past. And then there's no homework tonight. And of course, we're going not to meet Wednesday or Thursday, back on Friday. There will be some assignments here as we start nuclear chemistry. So let's get crazy and complete this form, or at least complete this chemical reactions. Okay, so we were talking about two types of reactions. We're talking about addition reactions, okay, and that was, of course, on your form. And so we're talking also about substitution. So in substitution reactions, we talked about, we have, of course, a substitution going on between one of the chemicals and one atom of a reactant and another atom of a reactant. Of course, that has to occur because this has to be a saturated organic compound, meaning it has single bonds between the carbons, which means there's no room to add on, there's no double bond. So in order for Cl to go on, an H has to go on. So the key here is we have two products, and this is saturated, okay? So in addition reactions, you notice we have an unsaturated hydrocarbon, either a double bond or a triple bond between the carbons. And that means if we open up that pi bond, we know that we can add everything to the carbon. But notice the new atoms have to go on different carbons, because as we open up that, or take away that pi bond, okay, that second bond, we now have an opportunity for both carbons along that double bond to add one more element, okay? So that's how that works. You can't add both to the same carbon, all right? So any case, one product, and I talked about halogenation, we talked about hydrogenation. What we do is to make a saturated fat, unsaturated fat becomes saturated, okay, corn oil into margarine, okay? And we did all that, and so we're moving on. We looked at sample problems, and you had a form that reviewed that. All right, so back on our horse here, or your pony, except my pony is always hurting when I ride it, although I've heard there's big ponies, I'm not really sure. All right, any case, fermentation is your next organic reaction. For those AP Bios, remember out there, we know fermentation is a type of anaerobic process that we get from getting energy, okay? So fermentation means that glucose, okay, gets oxidized. Remember, CO2 is the most oxidized form of carbon. So glucose gets oxidized, and we know that NAD, okay, plus grabs some electrons and hydrogens, and those NADs get recycled by the carbon frag becoming glucose. So it's more than just one step here, okay? So fermentation is a process which recycle, okay, our electron carriers. Remember, the electron carriers actually go into the mitochondria to support aerobic, okay, cell respiration, and therefore get a lot more ATP, 36 ATP, as opposed to 2 from glycolysis. So if glycolysis is running without the oxygen in the mitochondria electron transport chain going on, or the Krebs cycle going on, if you remember that, the only way for that to keep going is to recycle the NAD+. Okay, and the only way that happens, normally electron transport chain takes the NADH, right, and grabs the proton and the 2 electrons, and then sends back the NAD+, okay, out into the cytosol where glycolysis takes it in, and that can keep going. But if there's no oxygen and there's no electron transport chain or Krebs cycle running, the NAD plus doesn't get recycled back. So fermentation helps along with that. And of course, there's two types. There's lactic acid fermentation. Remember us, we gave off lactic acid, which is a lot like the alcohol, but we actually can reuse it. The liver converts it back, okay, into pyruvate, which can enter the mitochondria at a later date. Of course, simple organisms like yeast don't have that organ to do the complex reactions. So what they do is produce alcohol, and when there's aerobic conditions. They do also have anaerobic conditions when they don't have oxygen. Okay, any case, who cares? The bottom line is glucose, C6H12O6, okay, becomes two alcohol molecules. In fact, this is ethanol, 2 carbons, OH, table R, and of course, 2 CO2. So how does sugar become ethanol? Well, zymase is an enzyme in yeast that helps this process along. Okay, so when we ferment sugar to make alcohol, and we do this in every alcoholic beverage, in order to make beer, wine, or liquor, this is done. The process might be slightly different how we purify or slightly purify the process. And what's the starting ingredient for the sugar? In wine, of course, we use the sugar in grapes. And the more sugar in the grapes, the more ethanol we have. So grapes, and we see this in Long Island, we have a huge grape or wine industry. We see this in the fall when the grapes are sitting, and people actually will measure the sugar content or the glucose content, all right, in the grapes, and they want to maximize the amount of sugar that's in there. So they sit out all summer, they grow, and they're, of course, photosynthesizing and grabbing the CO2 and taking the energy in, but they're making alcohol. Okay, now when they take the grapes, when they have the maximum amount of glucose, then they harvest them and they crush them, and eventually they add yeast and they ferment them. Okay, and of course that's the wine. They let the CO2 leave. If it's a wine that keeps the CO2, that's called champagne. Beer uses hops, but it's a type of grain. Grain alcohols, okay, whiskeys, okay, they could use corn, they could use different types of grains, okay, and of course liqueurs, where they have like peach schnapps or blackberry brandy, they used what? The fruits. Bottom line is they need to somehow do what? Ferment it into alcohol. So sugar, alcohol, and CO2, it's just nothing more than memorization. And I probably gave you way too much there. Okay, combustion. Okay, we've learned about combustion as being an oxidation process. Well, fermentation is also. So any case, you notice in combustion, we take oxygen and we take an organic fuel. Table I, as we've talked about before in your Regents reference table, lists in the top third combustion reactions. And these are an example of organic reactions. Now, don't forget, we undergo a slow oxidation process of our glucose in cellular respiration. So combustion is an organic reaction because most of our fuels come from fossil fuels. Fossils, past living organisms that have carbon. Living things are carbon collectors. So we've got a lot of ways to oxidize this. Notice when it gets oxidized, the C2H5 becomes CO2, the most oxidized form of carbon, and water. Carbon and water are the two reactions. So that's just something to identify as well. Easy, we've been through combustion, burning carbon-based fuels. Okay, so now we're gonna go on to, and it's anaerobic respiration, sure. Polymerization, there's two types, okay? Now what is polymerization? Well, you've dealt with this a little bit in bio, but polymerization is when you take two small monomers. Monomers represent the smallest unit that repeats over and over again. Okay, and so polymerization is this monomer. Now this monomer right here that I'm showing in this example represents an amino acid. It's got a Cu group and a carboxylic, that's the acid part, and then it's got an amine group, an amine group. There's the amino, and here's the acid. Notice this is the carbon, the secondary carbon, and this is where the R groups are. So these are two different amino acids. And when these guys collide with the right orientation, water comes out. So they call it condensation polymerization. Hey, you think about condensation, have a soda can on a warm day, or even on a lukewarm house, you put a soda can or a carbonated beverage or whatever on a on your shelf or on your table, you're going to see little bubbles of water. They look like they're coming out of the can. Absolutely not. Obviously, what's happening is the water vapor in the gas phase hits the cold can, the refrigerated can, and condenses into water droplets on the can. So water is being physically appearing in condensation. Here it's chemically appearing as the H from the amine hits the OH from the carboxylic acid of two different amino acids, and water comes out. So anytime we have monomers, single units that have H's, okay, and OH's, or have the ability for water to come out and then link them, we call it condensation polymerization. By the way, have we talked about ester formation? Haven't we talked about the alcohol part and then combining with a acid part, and that makes an ester? Well, have anyone ever heard of a polyester? Yeah. Well, one big part of clothing, a synthetic part of clothing besides cotton. Cotton is made of course, cellulose fibers. Okay. So is paper, by the way. Paper is not really. I'm sorry, not paper. So is money. Money is not actually made of paper. It's made of cellulose. That's why it feels different. It's made of cotton fibers. Okay. Any case, that being said, polyester is when you have more, keep adding more ester linkages. And then you know something about esters, and you put them together, the organic acid, the OH group, or the OH group from the organic acid hits the OH group from the alcohol, and water comes out. That's another example of condensation polymerization, as you make a polyester, many individual units of esters. Okay. All right. And so water comes out, and then we have what we call the peptide bond, which, polypeptides mean what? You have many amino acids. Okay. Now, you need to recognize your natural polymers versus synthetic. Silk is actually made from the silkworm. And so the silkworm creates a polymer, and this is the unit. Okay, you can see it looks a little bit, here you have an amine group, amide group right there, and you have a carbonyl carbon and an amine here. It doesn't really matter, but this is the single unit. And what they love to show in polymers, because they're incredibly long, you're never going to write the entire formula of a polymer because they can repeat thousands and thousands of times. So you would never write the molecular formula or the structural formula that way. What we do to show that this repeats over and over, we show brackets, and then we show this little number n to remind us that that repeats some number of times. So this is the monomer of silk. And as you can see, because one N has an O and another one has an H, you can see that the silk, when it comes together, is going to produce a water. That's how you do it. And it's part of condensation polymerization. And of course, silk is a natural polymer. Proteins are a natural polymer. Okay, you may have learned in biology glycogen, which is basically glucose stored as a simple starch in our liver, okay, to keep our bloodstream full with the right amount of glucose. Glycogen is glucose bonded to glucose, is a polymer. Proteins are a natural polymer. Cellulose, which is glucose bonded together, but every one is flipped over in a beta linkage, okay, that humans have an enzyme to break down. That's dietary fiber. That's a natural polymer. There's rubber, the first polymer that we actually got, okay, that came from trees, okay, we made tires from. That's also natural polymer, okay. All right, and then we have our synthetic polymers. Dacron was I think Dacron was the first synthetic polymer, okay, or Bakelite was, I'm not really sure, but notice it doesn't really matter. Look what comes out, water, okay. And then we have nylon, which I'll show in a demonstration, is also a monomer with an OH and an H, so they come out and they create look at this, an amide linkage, right? So nylon is another. And a lot of these synthetic polymers were made by accident, okay? Teflon, everyone's got Teflon in their, I don't know, somewhere in their cooking pans. You have Teflon coating, which is a non-stick coating. That is a polymer that was made by accident. So there's a lot of these type of unnatural or synthetic polymers. But the bottom line you need to know is that individual units come together, water comes out, condensation polymerization. How do I know? Look at your monomer and see if they have that. All right. In any case, here's polyester formation. Okay, and this is showing the linkage. So I'm just going to play this. All right, and I don't think you're going to hear any. I'm just going to take this down. Hopefully, I have internet at the school. And the circle goes circle. There we go. So, hey, oh, the water comes out. I make a C double bond. Hey, there's a what? Ester linkage. Oh, here comes another water comes out. Another linkage. Oh, here we go. Actually, that's not an ester linkage. It's some kind of, hydrocarbon chain, but there is an ester. So, bottom line is water keeps coming out as we make the ester linkages, okay? And so this is a polyester. Notice the ester repeats over and over and over again, okay? All right, and moving on. All right, I guess I'm trying to go forward to go backwards. We have polypeptide. This is another example of a polyesters are unnatural or synthetic polymers. Polypeptides, of course, are natural. Water comes out. Okay, this is the R group. Remember that? All right, this has an R group here too, and water comes out. You get the idea. Okay. All right, the nylon demo. Okay, I guess I'll stop here to show me doing it, not this. So nylon's really cool. Okay, you take two reactants. Okay, and what's really cool about this is that you can see the two liquid layers here. What's really so cool about this demo is that I'm going to take a paper clip, a little hook in the end, and I'm going to put this paper clip on the bottom, and I'm going to pull this through. So I'm trying to pull this liquid, one reactant through another, and then that's going to create the polymer. Okay, so it's kind of a cool thing. Now it's a condensation polymer, and I'll show you that. Monomer in a second. So let's just stop talking and play it. Yeah, title, great job. And oh, Christmas, hook on. Here we go. So I'm going to put that through. Now watch as I pull that through, and I create the polymer, and there's a nylon. I think that's what makes the stockings, okay? And I can keep going up and up and up, and if I don't break it, I can go on, and you can see it's really kind of cool. You can see I'm pulling one layer through another. Demos like this maybe love chemistry, the magic of it. So I'm just pulling one layer through, and I'm just actually going up, up, and up, and I'm going to show you that in a second as I keep pulling up, up, and up. All right. And there's my polymer. That long chain of monomers is making that long string possible as I keep turning and turning and turning. Okay. And I don't think I have any more room. And I could run that down the whole way if I was to turn this glassware. Okay, so kind of cool. Here we go. I'm still pulling more and more. As you can see, this polymer is getting longer and longer as I pull that through. Pretty amazing. Okay. I think that's a pretty good demo to show how monomers, okay, were linked together from those two liquids. I'm just pulling that through. All right. So kind of cool. Oh, I broke it somehow, or I ran out of the reactant. So there it is in all of its glory. Probably ran out there, the top layer. Okay. Cool beans. The beans are chilled. All right. Let me show you something here. Really cool little PDF I got from David A. Katz. Okay, so he's talking about the first natural polymer here is rubber. Now look at this, rubber 1, 2, 3, 4. Look at the name of this, 2-methyl-1,3-butadiene. Whoa, on the first carbon, okay, and the third carbon, there is a what? A double bond. That's what's the butadiene, and then therefore, remember the double bond takes precedence. So the second carbon, oops, this one's the first carbon. Second carbon is the methyl group, and this is an example of the what? The monomer. Okay, so that's kind of cool. Now notice, if rubber is a natural polymer that we got from many trees and made the first tires and so forth, you notice there's no OHs in this. So this could never ever have stuck together by condensation polymerization. Okay, this would have to be stuck together by opening up this double bond. And if you can guess it, anyone guess what type of polymerization this is? This is not condensation polymerization. This monomer has no OH on it. So can anyone guess how this might stick together? Normally just Cole responds. So Cole, I'm leaning on you hard again. Anyone guess? how can this stick together with another one? What has to happen, you think, to this double bond? Well, the double bond has to open, and then we can add directly. This would be addition polymerization, okay? All right, any case, let's go back to what I was talking about, and that was my nylon. Now look at all these monomers. Pretty cool stuff here. I don't know where my nylon is. Wait a minute, did I pass it? Nylon, there we go. So there's my nylon, and there's my monomer. COOH ending, so a Q group at the end. I have CH2 some number of times. So look at this, this monomer actually has 2 Q groups on both sides. So you can guess when another monomer of nylon hits, you can see the water comes out, and look what we have here. Here's the 2 monomers, right? I'm sorry, there's 2 monomers here. There's the double carboxylic acid, and there's the double amine. So if you notice something, what did I pull through? Did I pull through 2 liquids? One of the liquids was this right here, and the other was this diamine, okay, compound. And I pulled one through the other. That's how I made it. One liquid was one was the other. I believe this was the top one, okay? And I pulled them through, and this N with H's hit this OH to make what? Water, because you have an H and an OH, and look what you got here, an amide linkage. Okay, polyesters. These are the polyesters in our clothing of a benzene ring. Look what we have here. A Q group. Oh, and an alcohol, because esters are made from what? Organic acid OHs. What comes out? The water, and there's your ester linkage. Okay, and there's all different types of polyesters. Okay, then there's cellulose. We have a glucose bonded to each other. There's silicones, and you say, what's a silicone? The silicone, a lot of the silicones are what we use, okay, on our homes, okay, as we caulk, or we put a liner, a bead in between like wood, all right, so silicone, and that's a linkage too. And then everyone's heard of polyurethanes. Polyurethanes are like shellac that we put on wood to protect it. Also, polyurethanes are also foams, filling foams. A lot of insulation now, they put foams in gaps, okay? But look at the ending here, CO, CO, and then you have the water have it coming out. And look at polyurethanes, there's a carbon double onto an O, and then you have an OH, so clearly water comes out here. And so these are all examples of having some kind of OH or O exposed in the reactants, okay, to give the polymer with water coming out. I'm gonna stop at polyurethane because guess what? I want to show you a polyurethane demo. This is something you guys saw in class. So I want to play this one. Now this was nylon in the beginning, okay? And we don't need to hear that, okay? So let's go to a polyurethane demo. I'm dressed so nicely today. And so what I did in this demo is I added 2 reactants, maybe. And I poured them in there. There's one. Okay, I think I was the first one. So yeah, there's my polyurethane polymer. And notice there's 2 chemicals here. All right, there's one with a carbon double bond to O to double bond to an N, and then there's this kind of dual or a diol here. Okay, ethylene glycol looks like, or actually it's a CH2N, so I don't know how long that chain is. Okay, so there comes one of the 2 chemicals. Okay, and I'm just kind of going to add the other chemical. I think I just did there. Doesn't matter, I added both in there. I stir. Okay, I got a spoon. Now it's hard to see, but if you keep going, okay, the foam actually starts to rise. And the reason why it's rising is that these 2 liquids are pretty compacted. And now what's happening is they're linking. And as they link, there's gaps, right? As a liquid, there's no organization. But as they make a polymer, there's definite organization. So there's going to be, it's going to be able to expand, take the unorganized liquids and start expanding outward. So we're expecting that to do that. All right. Although so I think you can see it in here. Okay. Now it's getting higher. Oh, Christmas, it really got higher. Okay. So it's hard to see where it is in the cup. Okay. But at some point, all right, it starts going above the cup. All right. this polyurethane foam starts expanding out of the cup. I don't know if that's a line is there or not. Okay, I feel like I went too far. All right, and yeah, definitely that line was there because it's disappearing. So it's getting close. It's expanding up. I should have shown on the top, and it should be getting to the top of the cup. And there it is. You can see it a little bit coming right at the top. And as my spoon there, and you guys have seen this demonstration, I kind of keep it, people look at it all year. Now I'm just going to put the spoon in. Again, it's expanding as it makes a polymer from the unorganized, very dense two liquids to a nice organized structure with gaps in between. And that's, again, a condensation polymerization. You may say, well, where's the water? This is very exothermic. So this is very warm. So I'm guessing that the water vapor is being emitted. And there's probably some water left in this, okay? Any case, you can see what's happening. Yeah, it kind of expands out. And interesting enough, it becomes very firm very quickly. So this is what we use to in gaps in foam as we shoot, under a sill to prevent, air from coming in. These are the type of things you use, a polyurethane foam. What's really cool is this warms up pretty good to the point where you can actually pick it up. Oop, I just did. And throw it around, okay? And this becomes really cool. All right, so this looks like I don't know, some sort of float or some kind of form of dessert with but it's not. It's a firm polyurethane foam that you can pick up. And you guys have seen this all year long. I would have done this live for you, but hey, all right, there you go. All right, good times. All right, I think eventually I do pick it up, maybe. And it should be warm enough after a few minutes and pretty firm and not sticky. And I just didn't want to hit my hands on there. I'm sticking there. Yep. So cool beans if beans are chilled. All right. So back to it. So that's another example of what? Of condensation polymerization. All right. But there's another type called addition polymerization. Hey, addition polymerization is where the monomer has double bonds, which means once you open up that double bond, you've got room to add. So two ethylene molecules can come together and open up that double bond, which means remember that pi bond is out there. And pi bonds, those electrons are susceptible to be attacked and broken. Hey, we talked about Teflon. Hey, Teflon is just a repeating unit of carbon-carbon. Notice, in addition polymerization, party people, what happens is the product is saturated between the carbons, single bonded. So Teflon, here's the monomer that repeats over and over again. Classic example of showing a molecular structure of a polymer. They call it polytetrafluoride ethylene, okay? PTFE, who cares? That's on the nonstick portion. Why it's nonstick is because the strong bond between fluorine and chlorine, this is not gonna bond to anything else, so it's not gonna stick, all right? So in any case, this starts as a double bond. That's the monomer there. All right. So here's an example of addition polymerization. Notice we're dealing, now we do have some little extra part that starts the ending and finishing the termination part, but notice the monomer is a double bond. Okay. And so let's play this. Eventually, the wheel in a circle. Okay. So now we're going to play this and we're going to, again, we have two little ports, and this little radical here opens up, and now this radical can attack the what? The double bond here, and that's how it works. Okay, that's a one extra electron. Notice we needed to start it, okay, and then of course there's termination at some point. Notice two chemicals were needed. Has everyone ever seen the epoxy that has two chemicals that you push together? Same idea here, okay, but notice that that was a saturated hydrocarbon there, okay. Okay, esterification, okay, we've talked about that, okay, but before we go to esterification again, I want to go back to this David Katz's polymers again, because it's a really great one. So these are all examples of addition polymerization. How do I know? Look at the monomers. Okay, here I've heard of polyethylene. It has a double bond, but once it bonds and opens up the double bond, you can directly add to the chain, thus addition polymerization. Common use or common polymer used in bags, wire insulation, squeeze bottles, polypropylene, indoor-outdoor carpets, bottles, polystyrene, styrofoam. Remember the styrofoam that I poured the acetone and I watch it decompose there? Styrofoam. Okay, by the way, to make styrofoam, they foam it by pushing CFCs through it. So they don't, so styrofoam is made very light with air in it, but a lot of that air was initially carbon tetrafluorides, right? CFCs, carbon fluorocarbons, I should say, okay, which are bad for, of course, the ozone layer. So styrofoam has this benzene ring. Notice the double bond. Open that up, this keeps adding and adding. Hey, PVC pipe, that's that white pipe that I had. Okay, you heard of PVC pipe. It's a white plastic, okay? And notice it's gonna what? Have a chlorine, that's the chloride part, but that carbon to carbon double bond opens up, addition polymerization. Here's Teflon. Notice it has what? 2 double bonds into a single bond, okay? And there's some other ones, okay? Acetates on films, natural rubber from the rubber tree, okay? That kind of started the tire industry, okay? Went into third world countries to process and get, and you know, almost was clear cutting these rubber trees until they figured out how to make it at some amount of time later, okay? Any case, examples of all polymers. Now, interesting, before we finish our work on polymers, for those that, and hopefully all of you want to save the environment, one of the issues with recycling these polymers, which we know as plastics, is that they do not have the same codes. If you take a bottle, okay, and turn it upside down, you will see these recycling codes. And one of the problems of recycling is that not only do we have to grab back the plastics, and hopefully the people who have the plastics don't just throw them in the woods or in the oceans, oh my gosh, all right? The problem is not only do we have to collect them from these individuals, we have to separate them. They're made of different what? Different monomers. So we can't mix them and melt them back together. So what we have to do is we have to separate them. So we have recycling codes. So peat, okay, polyethylene tetraphthalate, or peat, is very famous plastic. This is the plastic in soft drinks, other beverages, okay? Milk containers are high density polyethylene. Okay, so the numbers on the bottom, some people think that's how many times they've been recycled. No, the numbers on the bottom tell them the type of polymer. So that when we recycle and melt them back down, we're dealing with the same ingredients. You can't, if you were to mix different monomers or different polymers together, okay, you'd render that whole batch useless. Okay, so the problem of getting the plastics back or the polymers back is number one. Two is then we have to do what? You have to put them and recycle them. It's man hours to look at what type of plastic they are and separate them. It's just highly, very, very what? Labor intensive. And that's why recycling is expensive. And that's why a lot of companies, you know, don't do it, unfortunately. Okay, so something to think about. All right, moving on. We're almost finished, party people. All right, so esterification, I'm not going to spend time on it, but we know we make esters. We talked about how you name an ester is based upon the alcohol and, of course, the what? The Q group that we, the organic acid and the water comes out. Of course, we make polyesters, ethanoic acid, methanol, and of course, methyl ethanoate, and that is a what? A very, very important aromatic compound, sweet smells. Okay, last little one here, and this is the one that's probably the most complicated, is saponification. Saponification is making soap molecules, okay? And I want to talk a little bit about that. But you should know that fats, lipids in your body are stored as fatty acids bonding to a glycerol molecule. And they stick together. It's called a triglycerol. This R is a CH2, CH2, CH2. And I want to make sure we understand this. Okay, you may have hit this, but we're going to hit it again. So I'm going to draw. Okay, here we go. Okay, so this R2 is really a CH2. And I'll just keep it straight for now. CH2, CH2, and this goes on for 35, 40, 50, okay, and it ends. So there's three of them. Now, what is a fatty acid? A fatty acid, as you can see, is an acid ending. So it's got a Q group. And then it's got this long hydrocarbon chain that I just drew. Now, if it's a saturated fat, now I'm just drawing a very small chain, but this is like 35. Long or 40 or 100. The saturated means you have single bonds between them. So saturated fats look like this. Now you say, Mr. Grodsky, fats I thought were nonpolar. They are. And they're nonpolar because they have a very, very long hydrocarbon chain. I'm not showing that here. So if you think about 35 of these carbons long, you would say that, hey, this molecule has a large, large nonpolar factor. Yes, there is a polar factor here, but it's inconsequential to the rest of the molecule, okay? And now, fatty acids, how fats travel or lipids travel in our bloodstream. Now, what they do is they bond to something called a glycerol molecule. Now, a glycerol molecule is an alcohol that has 3 alcohol groups. And their OH is here, OH is here, OH is here. In fact, the name of this, we named this once, okay, was 1, 2, 3, prop for 3 carbons, ane because of single bonds, but because it's an OH group, it's a propentriol. So this is 1, 2, 3, propen, take the E away, propen tri, because there's 3 OH groups, all. And so it has 3 OH groups. And what happens, party people, you guessed it, okay? An ester comes out, or I'm sorry, a water comes out, and these link. And they make an ester linkage. That's what this is here. So you make ester linkages. So fatty acids make a 3 ester connection with 1, 2, 3 propentriol, which by the way is glycerol. And this is how we store fats in our adipose tissue. Okay, it's important to realize. So what is saponification? Saponification is where you take a trihydroxyl alcohol and you cleave them with a strong base. So I'm going to clear all of this and we're going to go on to the next page. Okay, mouse. And there's my ester linkage. Okay, so saponification. Again, really you just have to identify it, but the key here is understanding that we're taking a triglyceride. Notice there's 3 of these ester linkages onto a propane backbone. We're going to use a strong base. The Na plus is just a spectator. It's the OH minus who actually breaks up and cleaves the 3 esters. And those 3 esters linkages, okay, notice there's, in this case, the fatty acids each have 17, okay? Notice what this is right here is that we have, I'm gonna draw it so you understand, okay? Remember, we're dealing with 3 of these, we'll go back here. We're dealing with 3 of these, so 3 fatty acids linked to a glycerol, and what happens is we get this long hydrocarbon chain. Remember, there was an ester here. The fat breaks the linkage, water comes out, and you're left with the conjugate base of the ester, OH minus. The Na plus, even though they put the Na here, that really, I mean, it's going to go anywhere it wants to, but it's a spectator, so they put that here. Na plus may attract the negative, or the water does. Okay, that's really not important, but we know that's a spectator, so it's not going to make a precipitate at all. But in any case, the bottom line here is that you're going to make 3 of these, because remember, there was 3 fatty acids. So this is a soap molecule, and what makes it a soap molecule is that we have this polar head, or hydrophilic, and this end can what? Deal with water. So water can attract this head. And then we're going to have this long, remember 17 carbons in this example, and there's 3 of them. We're going to have this long hydrocarbon area, and this is hydro, what? Phobic or nonpolar. And this long tail is what tracks fats. So what happens is, it's really cool. Okay, and I'm going to stop here for a second. All right, here comes my mouse. I'm going to stop my share, and I'm going to go to a whiteboard. I'm going to share my screen again, and we go here. Okay, what we have, so if I have your skin, okay, not your skin, that's kind of weird, okay, and we'll go here, skin, and we're going to have a follicle of hair, you know, and then we're going to have a fat molecule. Yeah, some fats. Now, we do have oils that come out of our sweat glands. So we know that water vapor, actually a little bit of urea, which is a component of urine, comes out of the sweat glands. But also we produce fat oils. And those oils that come out of the epidermis are there to keep our skin. There's a layer of fat and oils that we produce in our epidermis, okay? That's a protective barrier so that we don't lose water. But those oils come to the surface as well through the sweat glands, okay? So we have some oils and fats that naturally occur. So I'll just do this as a fat globule, okay? Now, of course, if we get fat on our hands, whether we're dealing with oils, painting, you're a mechanic, and you have these oils or fats, or we know these are nonpolar. Now, if we ran water on top of these, of course, the water is a polar molecule, as we already know. It's bent, sp3 hybridized, whatever. It's got a negative, partial negative side and partial positive side. This has nothing to attract. Now, we do know that water has a cloud of electrons, but it can't effectively attract this fat and pull it away. So water just kind of runs over this, and water alone won't take away these oils. So what we do is we add fat molecules. Now, I'm going to draw the fat molecules. Now, how fat molecules made? They're made from, they have a polar head. Okay, so this polar head you should recognize to be the what? This ending, which is after the ester has been cleaved by adding water. And then they have a non-polar tail. And that non-polar tail is the what? Hydrocarbons that continue on in the case that I showed you, 17. And so when we use soap, what happens to the soap is the non-polar tail will jump and be attracted to the fats. So they call something called a micelle. So all the non-polar tails jump in, and the polar heads of these fat molecules stay outside. And they deal with the what? With the water. The water, H2O, can attract these. And so the water attracts all of these heads here, and then when you wash the water away, the water can pull the entire, what we call a micelle, which is a collection of soap molecules. All right, so it's pretty cool. Soap works. Now, we know if we use too much soap on our skin, it can actually dry out our skin. Okay, so it's got to be careful. Sometimes in soaps we put back, but the first soaps, we took animal fat. Okay, and with the animal fat, okay, we added a strong base, and the Egyptians were the first, we think, to do that, okay? And they put a strong base to animal fat and made soap. And one of the uses of the fats of whales, okay, was to make not only fuel, lamp oil to burn, but to make soaps as well. So be aware that soap is saponification. So I'm going to stop my share. I'm going to go back to and finish up here. Okay, share my screen, desktop, and back to reality. Okay, and so this is an example of saponification. Notice there's 3 fatty acid chains on this glycerol. You cleave them, 3 soap molecules. Here's the polar end, here's a non-polar end. And notice we produce glycerol. So what do you got to do here? Just recognize that reaction. Okay, moving on. I'm not going to play this. I play this for AP My Bio. And then we have some reactions, okay, here. All right, so let's just review a little quick. C3H6. Hey, double the H's as carbons, table Q. That's the key here. C3H6. Is that saturated or unsaturated?
Saturated.
Yes, coal to the rescue again. So therefore, well, it's actually unsaturated coal because it's got double the H's. Look at CnH2n. This is an alkene. If you draw it out, you'll see it. This is a double bond, right? So party people, if you forget, C3H6, 1, 2, 3, 4, 5, 6. Every carbon has to have what? 4 bonds. Only way to do that is put a double bond here, take this away, and put it here. So you need it 1, 2, 3, 4, 5, 6. C3H6 based on table Q. CnH2n double. So this is under the maximum amount, and therefore chlorine can directly add to this. So this would be an example of, okay, so many people responding. Clear all my drawings. Let's go mouse. And I just kind of gave everything away. So that's addition. Notice the chlorines are onto each, so adding. Now this is saturated. I'm sorry, O2 and C. Oxygens with a carbon-based fuel, of course, that's combustion. That X would be water. Notice in the first one, going back to the addition reaction, what's happening here is everything is adding to the chain because you have room. You got double bond to open. Notice there's only one product. That also gives it away. Here I have glucose making 2 ethanol, alcohol, okay? And of course, that's gonna be CO2, and that's fermentation. Here's C2H6. Hey, there's where you have 2 carbons, double the carbons, and then add 2. That's an alkane, that's saturated, which means what? 1 H has to come off from 1 Cl. So this, of course, would be 1 Cl adding, substitution. And then the last one we just did is where you had these huge fatty acid chains bonded to a glycerol, triglyceride with a strong base. We make 3 soap molecules, and that's saponification. And we also add glycerol there. Okay, so that's it. That concludes organic chemistry in all of its glory. Okay, we are done today. All right, please look for the homework, which of course for us, look for it posted next time we meet. Okay, actually look for it posted next Monday. All right, and we're going to stop the share. Hopefully I recorded today, and I hope you have a great weekend. And again, I replay this again if you're kind of lost a little bit. So Monday, nothing new. Monday, I'm going to post a new form based upon organic reactions. Have a great weekend. I'm going to end this, and I hope you're doing well. Bye-bye. Someone say bye.
Bye, thank you.
All right, thanks.